have a couple quick questions for you.
Okay.
And then I think Paul has a question about the lecture. But
Oh, yeah.
I watched the recording of you, Elise, and Katie discussing problem 4 last night from the homework. And that was the one where you were brought up the Euler phi function.
Yep.
And I was curious, do you have a preference on whether we use that function or whether we use the regular inclusion-exclusion principle for that specific problem? Is there a way you want us to see us solve it?
Well, I solved it in class. I mean, I gave the general formula in class using inclusion exclusion, right?
Right.
So I guess I don't care. I mean,
Okay.
you could redo. I mean, because you only are, what is it, like 730 or something?
630.
630. So you could just say, you know, I mean, you could just do it again. I guess is what I'm saying. But it wouldn't be very hard because there's just not that many numbers. What is it? Just like 2, 3. So 630 it's 2, 3, 5, and
5 and 7.
7. Yeah. Yeah. So I mean you could just rewrite the thing, but I mean you I don't care though. I mean we already did it
Okay.
for general in anyways.
That's true. So I guess
So
I was going to go with the Euler phi function because it's simpler and easier since we've already done the work. But I wanted to make sure
right.
that was okay with you first.
And the proof is based on inclusion exclusion. So
Yes.
yeah, that's fine.
Okay.
Yeah.
And then my other question for you was on 8.2 problem 3. The problem shouldn't be that hard, but I was really confused
Since
by
it's number
it.
3.
Well, yeah, it's an odd number, and I even looked at the solution. I'm like, okay, what's going on here?
Okay, let's see. Okay. All right. Got it. So what are you thinking?
Okay, so this is in the inclusion exclusion section, so we have to use that somehow. The tricky thing when I was thinking about this is that if there were only 3 of each type of number, or if the problem was set up in a way where we didn't have to worry about the 4 of a kinds, we would just arrange everything freely. And when we're worrying about, sorry, I keep somehow accidentally turning that off. But in this case, when we have to keep track of 4 of a kind, we're okay. Like if we place the first king, the second king, and the third king, it's only once we place the third king that we suddenly have less options. You know what I'm saying? So I didn't really know how to separate that and structure the problem.
So is your problem, I mean, I just want to make sure because sometimes if you have like the international version, the problem ends up
Right.
really different. Mine just says, what is the probability that a 9-card hand has at least one 4 of a kind?
Okay, yes. So that's what mine was. So I guess just back up a bit and say what I was. So when it says at least one 4 of a kind, I'm thinking we want to negate that and say no 4 of a kind, because that seems like it'd be easier to handle.
I see. Okay,
But
so you want to have no 4 of a kinds.
that was my thought. But I didn't know how to go about doing that.
You're saying like each A sub I would be like having no 4 of a kind of I kind, basically.
Of kind I.
Yeah.
And then the set that you're actually looking for would be A sub 1 complement intersected with A sub 2 complement, and all that.
Yeah.
I think
Would that work?
I mean, I'm pretty sure that's following the same formula that like a lot of those problems have been, and I think that would work because think about it. In order to have at least one of something, well, we don't really care how many there are. You just need to not have none of them, basically.
Yeah.
So
You could also, I mean, you could also do it as a union problem.
actually, yeah, that's probably better because the way I just described it, I think now that I'm thinking it through, that would actually make it so that you have one of each 4 of a kind, which wouldn't really make sense in a 9-card hand.
Right.
So
Well,
yeah, that
so like you could say, you know, A sub, or let's use S. Or no. Don't use S. What am I saying? S is reserved for something else.
mhm.
Uh, so let's use B's so that I could sub-index these by. I don't want to write A sub capital A. That's why for ACE. But like you could say B sub A is the set of 9 card hands that have all the aces. Does that make sense?
Yeah.
Okay. And then like B, what would B sub 2 be?
The set of 9 card hands that have 4 twos.
Yeah, that have all the twos. And then B sub 3 would be the set of 9 card hands that have all the threes.
Mm-hmm.
That makes sense? And then I think this is just a union problem. I mean, you're going to have 13 of those Bs, correct? But it's a union problem because what you're asking for is I just want to have all the aces, or what?
Oh, all the twos or
Or all the twos, or all the threes, all the fours, etc. And you can just straight use inclusion exclusion to do that. But you would use the union version of it. Does that make sense? Where you would first add up all the sizes of the individual sets and then subtract off all the double intersections, add back in all the triple intersections, etc. And by
okay.
counting any of those B sub whatevers is easy because they're all the same size. Do you see what I mean?
Yeah.
Right? Because
Um,
well, if I want to have all the aces, then I have all the aces, and then I just need 5 other cards. And you don't pay attention to what you create in selecting those 5 other cards because inclusion exclusion takes care of everything on the back end. So like if I want to count the number of things that have all 4 aces, I set those 4 aces aside, and then from the other 48 cards, I just go wild. I say, well, it's just 48, choose 5. Okay. So
okay.
B sub A, the number of hands that have all the aces is just 48, choose 5, right? And that's it. And what about like the size of the double intersections? That's easy to count, isn't it? Because they're so like if I intersected B sub A with B sub 2, well, that just means I have all the aces and all the twos.
Mhm.
Then
And
you only have
now all I have to do is choose one card. 4 ways to do that. Does that make sense?
Yeah.
And triple intersections, well, excuse me, you're going
Possible.
to be in trouble. That's going to be 0. Does that make sense? Because these are
Yeah.
9 card hands. So, yeah. So inclusion exclusion just totally annihilates this problem immediately.
Yeah.
And you don't even really have to think about much.
Okay. My initial reaction was to do it like Paul and to try to do it as a intersection problem. It was the way he set that up not going to work. Because the union's simpler, but
that was just my knee-jerk reaction. But then I realized, wait a minute, that's just impossible. We can't have all the pairs of 4 in a 9-card hand.
Well, so yeah, I mean, I think if you can set up an intersection in the right way,
okay.
to work out, but you would probably have to do like, I don't know, I'd have to think about that. I think thinking of this as a union problem is the way to go.
Okay. And then
see this or that, or this 4 of a kind, or this 4 of a kind, or that one potentially. They're asking about 8.2 number 3 right now.
Yeah. And my last question on that was looking at the answer key. Is that did they use the union approach or did they do something different? I was just curious. They have 13 times 48, choose 5, minus 44 times 13, choose 2.
I always get the back of the book in this book tends to be pretty accurate, doesn't it, for the most part?
Yes. But every once in a while, they'll use a different method than.
Yeah, that looks like what we just did, because 13 is the number of sets. Yeah. It looks like they used the union problem. 13 is the number of bees, correct?
So that's 13, choose one.
So you choose one of those. You know those are all going to have the same size. What's the
Okay.
8 choose 5 coming from?
That's all of the size 1 problems, right? Where you're picking, you
Yeah.
have one set of 4.
And then you just have to choose 5 other cards from the other 48. And then they say minus 13 choose 2. Well, that's the total number of pairwise intersections you're going to have, because you have 13 kinds. You choose 2 of them, and you're going to take all those cards, like the aces and the twos, for instance, and then
Yeah.
multiply it by 44. That's exactly what we said, right?
So where's the 44 coming from?
Well, because you still have to fill out the 9 card hand. How many cards do you have? The 13 choose 2 is you're just choosing the 2 kinds.
Okay. So you have to pick the one card out of the remaining 44
Yeah,
options.
the one remaining card. The 2 4 of a kinds account for 8 of the 9 cards.
Okay.
And 44 is just saying, well, I got rid of those 8 cards and I have 44 left. And the
That
reason
makes sense.
anything else is because you can't have a triple intersection if you only have 9 cards. And look, now you're like, there's no stopping you, because they could have said, well, what if I have, 17 cards? Well, then we would have just kept going, right? And it would have just been easy to extend that. So,
Yep.
yeah.
Okay. Well, thank you. That makes sense.
Yeah, cool. Did you have a
I
question?
think I'm going to head out, guys.
All right, see you
All right,
later.
see you later. See ya. See ya, Logan.
Bye.
Okay, so I just had a question for about the 9.1 lecture about the weird note, the difference in the notation between what the book does and what you do, about like the different usage of the permutations.
Okay.
So
Yeah.
I understood everything with like using actual. I don't know if that's inverted or not, but
No, that looks correct.
looks correct to you guys. Okay, it's inverted for me. I guess it's only inverted for me. But anyway,
Yeah, that's right.
I
Yeah.
understood everything through there, through how
Okay. Well, that's good.
when you put the tilde on top and start doing the like putting in the actual colorings instead of just like how it changes the vertices.
Yeah.
That's when I couldn't exactly tell like what's the correct usage of the tilde, and because the book doesn't use it, and I was trying to just reconcile what was going on there.
Well, because now you're not thinking of a function. So the permutation is a function, right?
Mhm.
And it was just a function on the vertices themselves when we gave those vertices labels.
Mhm.
That makes sense?
Yes.
Okay. But that function on the vertices induces like a function on the colorings, like C1 will go somewhere, etc. So
Mhm.
it induces a function on the colorings, but it's not I mean, pi3, all pi3 was doing, it's like just sitting there going, well, I'm just messing around with the vertices, I don't know, right?
Yeah.
Induces a function on the colorings where the colorings are flowing into each other, but that's technically a different function. Does that make sense?
Okay.
It's moving the colorings around, and there's a lot more of those. Yeah.
Right.
So that's why I was hesitant to use the same letter, because that's correct. Does that make sense?
Okay.
It induces a new function on the colorings. It is, in fact, it is a completely determined by pi3, but it's still not the same function. It's not even moving the same number of objects around. It's moving 16 objects around now.
Right.
Yeah. So that's why I put the twiddle on there, just to say, look, I understand that they use the same thing, but to me, they're conflating two different entities. Yeah.
Right. And does it work the same way? My other question was, does it work the same way when you are doing the compositions? Like you would keep it without the tilde if you're looking at it in terms of the vertices, like when you have the 2 cycle notation side by side and stuff like that?
Yes. Yes.
But then you would do it with tilde if you were looking at the same thing, but with the colorings going back.
Yes. That's exactly right. Yes. So do you see, Paul? They're technically two different permutations.
Because they have different domains, basically.
Yeah, that's exactly right. Yeah.
Okay.
Yeah. Yeah.
Okay, that makes sense.
You see how the one induces the other?
Yes. Yep.
Okay. Yeah.
Yeah, I could tell how they were related, and I could tell what the book was trying to say. Like,
Yeah.
pi 3 imply like if you plug coloring 3 vertices in, you get the vertices of this color, basically. But they were just shorthanding that in a way that made it like,
Yeah.
it made it like what you were saying. You're putting in and getting out something different than what the function was actually.
Yeah. That's exactly right. They're different functions, definitely related, but not the same thing. And also, this is the section of the book that I think it's one of the most beautiful parts, but I do think they make some unnecessary compromises in terms of precision.
Mhm.
And this is one place where that starts. I mean,
Right.
I showed that to Dr. Fry. I mean, he would look at that for 8 seconds and just literally pass out. And then you have to wake him up. And then he would look at it again and pass out again. And then after a few times of passing out, he might start to say, okay, I think I could fix this. And I think that what he would do would probably be what we did.
Gotcha. And so, okay, and then therefore it still would not be fair technically to say, like for example, if you said pi 3 this is just using one of the relationships that they gave in the book, of the fact that under pi 3 the vertices of coloring 1 remain unchanged. But it still would not be fair to say, let me circle that. It still would not be fair to say this at the bottom, right? Pi 3 of C1 equals C1. That's still not
No, it would be pi 3 twiddle.
fair. Right, okay. Okay,
Yeah, because pi 3 twiddle is the thing that's operating on the colorings.
right. Okay.
And the other thing I did that differs from the book, this is just, I mean, to me, I mean, this might, Dr. Fry might actually die if he saw this. But like the composition business,
Yeah.
where they plug in the coloring, but then they read the composition left to right, as opposed to applying it to
Oh, right.
the function first. I don't know why they would choose to do that. I mean, that literally took me a half hour. I forget this every time, but it took me a half hour to figure out what is going on, because I was just doing a composition.
Mm-hmm.
Make sense?
Yeah.
Saying that is not what I get. What is happening? And then I realized what was going on. So that composition business is just inexcusable in my estimation. So that's why I'm doing this weird notation, just so that the book, like the things that are happening in the book, match up what we're doing. That's why I'm applying like the coloring on the left of the permutation. Does that make sense? You remember to first apply the leftmost permutation to the coloring, look at the result, and then apply the next one to that result.
Okay.
Makes sense?
Yeah.
Okay.
Yeah, that helps a lot. Yep.
Okay. So just be on the lookout for that. That's a little tricky nuance that that comes up. Yeah. Dr. Fry wouldn't die, but he would definitely pass out at least. Yeah. Okay. All right. What else? Did you have something, Katie?
Yeah, I had a question about problem 10b in 8.2.
All right. Yeah. Okay.
So I was able to do A and C, but with B, you've got that negative in there. And I seem to remember back when we were talking about generating functions, you said if there's a negative, there's some way to kind of like shift everything, but I wasn't quite sure how that would work with the negative in there.
Why don't you just add 10 to everything?
Well, that's what I was wondering if I could do. Yeah.
Yeah. Yeah.
Okay. So add 10 to each of the x sub i's. Am I going to have to add 40 to the 28?
Yes.
Okay. That's what I wasn't quite sure on.
Then you're going to have new variables,
Okay.
yi, which are xi plus 10,
Okay.
those those new variables are between 0 and 30, not
Okay.
inclusive.
Hmm.
And then you're just back in one of the old school,
Right.
well, you're not, then you're just going to be able to use inclusion, exclusion,
Yeah.
donut problem or something, right?
Yeah. Okay. Cool. I just wasn't quite sure, yeah, with adding 10 to each of them, how that affected the 28 and all that. So perfect. Cool.
Yeah. We have lots of freedom. In fact, you could, it does, they, they didn't even have to say that they were all between -10 and 20. They could have like done some weird
Mhm.
ranges for each one, and you still would have been able to fix it. Like you could have
Mhm.
been going down to -5, and you could have said, well, I'm going to add 5 to that one.
Mhm.
And then you could look at what that does to the overall equation, but
Mhm.
you would be able to reduce it to a donut problem.
Okay.
Yeah.
Great. Cool. Thank you.
All right. Is that all you guys had?
That's all I had for now.
Yeah, I think I'm good for now.
Oh,
Thanks, Dr. Hammett.
all right. Cool. Good to see you guys.
Good to see you too.
All right. See ya.
Bye.